All right. In a problem like this, the first step you need to, uh, again, you need to choose which way you're going to approach this. I'm going to approach this with the first method. I'm just going to combine each numerator, or each of the numerator and the denominator of the overall complex fraction as individual single fractions. So I'm going to kind of work to separate these two. Okay, so let's start in the numerator. If I look just at the fractions in the numerator and find the LCD, based on my first fraction, I need a factor of x. My second fraction, I need a factor of x squared plus 1. X squared plus 1 doesn't have any additional factors, so I don't need to do anything else with it. Okay? So what I'm now going to do is take the original fraction, first fraction's numerator, multiply that by the LCD factor that's missing from its denominator, has the x, it's missing the x squared plus 1, plus the next fraction's numerator times the missing LCD factor from its denominator, it's missing the x. So if I rewrite, I'm just going to reorganize this, distribute my 1, so I get x squared plus 2x plus a 1. There's my numerator, leave my denominator as factors. And so here is my numerator written as one single fraction. Okay, I'm going to do the same thing in the denominator. I'm going to write it as a single fraction. So here as I work through my LCD, I need an x. And here in my second fraction, I can factor this first, take out a common factor of x. And so I see the LCD factors necessary based on this second fraction is x, which I already have, and x squared plus 1. So it winds up being the same one as the top. So I take the numerator of my first fraction times the missing LCD factors from its denominator, has the x. Again, it's missing the x squared plus 1. Plus my next fraction's numerator 1 times any missing LCD factor from its denominator. And the most common mistake I saw in working with students is they forget to see that the x and the x squared plus 1 are both in the denominator, so there's no other additional factor. You just leave it as this. So when we distribute the 1 and combine our terms, we get x squared plus 2 all over x times x squared plus 1. Okay, so here is our fraction written as one fraction divided by another. Well, we're going to convert this division symbol and turn this into a multiplication problem by inverting and multiplying. So if we take the numerator, and I'm going to go ahead and factor that it's a binomial square, perfect square trinomial, so x plus 1 squared over x times x squared plus 1. And I'm going to convert this into, instead of dividing it, to multiplying by the reciprocal. So the x squared plus 2 gets moved to the denominator. The x and x squared plus 1 move to the numerator. And now I cancel common factors. So the x's cancel, x squared plus 1's cancel, nothing else does. So I leave my numerator over my denominator. Okay. Now, I do have to account for some domain restrictions. When I look here, I see that x can't be a 0 based on this cancel factor from the denominator. Here, x squared plus 1 can't equal 0. And that value can never even be, can't even be a non-negative, so it's not even going to be a 0. There are no zeros for that. So I don't have to worry about it. The only other thing that I need to worry about is because we had a division problem where we inverted and multiplied by this, we have to check all of the factors from this numerator just to make sure that none of them equal 0. Since they're both canceled, those are accounted for in our simplified form already. So that's as far as you need to go to simplify that expression.